Hi everybody, Mrs. Pesic here.
And Miss Bella.
And we're looking at section 5.8, which is solving radical equations and inequalities. Our objective in this lesson is to solve radical equations, and that is the new vocabulary for this section, is radical equation.
So a radical equation is going to contain a variable within a radical. Recall we have two steps. We can solve a quadratic equation by taking the square root of both sides. So if we had an example like maybe x squared was equal to 9, we would solve that by taking the square root of the left, square root of the right, and we would end up with x equaling plus or minus 3, because that was the square root of 9. Similarly, we're gonna solve radical equations by raising both sides to a power. So kind of going the opposite direction there. So we have three steps that you're going to want to write down on how to solve these. Step 1, you're going to isolate the radical. So you can see in this example here, you're getting the square or the cube root of x by itself by moving the 2 over, adding it over. Step 2, you'll raise both sides of the equation to the power equal to the index. So this was a cube root, so you'll raise both sides to the third. And then step 3, we'll simplify and solve.
Okay, and don't forget, for a square root, the index of the radical is 2, so that's why to solve a square root radical equation, you would square both sides. All right, let's take a look at this first example. Example 1 is solving equations containing one radical. Warning! Raising each side of an equation to an even power may introduce extraneous solutions, so it's very important to always check your answer. So let's take a look at this first example. Get this one written down in your notes. 5 plus square root of x plus 1 equals 16. Our first step is to get that radical by itself, so let's subtract 5 from both sides. So we now have square root of x plus 1 equaling 11. And at this point, we need to do the inverse operation of inverse operation of square rooting, which is squaring both sides. So we're going to square both sides, and the square rooting and the squaring cancel each other out. So we have x plus 1 equaling 11 squared, which is 121. So to solve for x, we just finished by subtracting 1 from both sides, and our solution is hopefully 120, but of course we want to check, because just by squaring both sides here, we might have introduced extraneous solutions. So if we do our little check, 5 plus square root of 120 plus 1, is that equal to 16? We get 5 plus square root of 121 is equal to 16. Square root of 121 is 11, and we're looking like we're in good shape here. So we do like our solution of 120.
Okay, let's try example B here. 7 cube roots of 5x minus 7 is equal to 84. Again, our first step here is going to be to isolate that radical. So since it's multiplied by a 7, my first step will be to divide both sides by 7. So I will have the cube root of 5x minus 7 is equal to 84 over 7, or 12. I want to get rid of a cube root, so I need to raise each power to the value that was in my index there, which is a 3, so cube each side. Since cubing and cube rooting are inverse operations, I'm left with 5x minus 7 equals 12 to the third, so 12 times 12 times 12 is going to be 1728. Now, to solve for x, I have to get x alone, so I'm going to add 7 to both sides. I'm going to just continue this over here on the side. So I have 5x equals 1735. And to get x by itself, it's times 5 right now, so we'll divide both sides by 5 and have x is equal to 347. Now, again, I want to always check this. Since I did raise it to an odd power, it should work. Usually even powers is where we have trouble, but it's still always good to do a quick check to make sure that this works. So I would say, is 7 times the cube root of 5 times 347 minus 7, does that equal 84? So again, I'd have 7 times the cube root of 5 times 347 is 1728 minus 7. If I'm,
sorry, 1735 minus 7.
Take that back. 1735 minus 7, so 7 times the cube root of 1728, which is 7 times 12, which is 84. So this works, and my solution is good, that x is equal to 347. So this takes you to your first must-do. Again, you're going to solve the equation for x. Remember, that is a square root there. So the power is 2, so you'll need to square both sides once you get the radical by itself.
Okay, let's take a look at example 2. This time we have equations containing 2 radicals. And so you do want to make sure that you have one radical at least isolated by itself. And in this case, we've got one radical here by itself. And this one over here is just times 3. So we are in okay shape to go ahead and square both sides, which is the inverse operation of the square root. So the square rooting and the squaring are canceling each other out. So on the left we have 7x plus 2. Now on this side we really need to do 3 squared times the square root of 3x minus 2 squared. And so we end up getting 7x plus 2 equaling 9 times, again, the square rooting and the squaring are canceling each other out. So we get 9 times the quantity 3x minus 2. If we distribute the 9 here, we get 27x minus 18 equals 7x plus 2. And now we're just solving a nice linear equation like you are very comfortable with. So I subtract 7x from both sides, add 18 to both sides, and I end up getting 20 equals 20x. So it looks like x is equal to 1. Again, let's do a check to make sure that that works. So if we do a check of 7 times 1 plus 2, is that equal to 3 times the square root of 3 times 1 minus 2? Well, here 7 plus 2 is 9, square root of 9 is 3. And on this side, we get 3 times square root of 3 minus 2 is 1. That's equal to 3 times 1. And we're looking good for a solution being x equals 1.
Okay, let's try another example where we have radicals on both sides of the equation. Again, as mentioned before, we want to try to isolate one of them. We notice over here on the left we have this cube root by itself. So we're going to start off by doing the inverse operation. Since it's a cube root, we are going to raise each side to the 3rd power, or cube each of those. On the left, a cube and a cube root are going to cancel each other out, so I'll be left with x plus 6 on the left. On the right-hand side, I want to remember that I'm cubing both of these values. So I'm cubing the 2 and I'm cubing the cube root. So this is really 2 to the 3rd times the cube root of x minus 1 to the 3rd. So simplifying what I have on the right-hand side here, I'm going to have 8 times the quantity x minus 1, or 8x minus 8. Again, I'm getting that by distributing my 8 through to that side. So bring down the left, x plus 6. Again, that leaves me with a nice linear equation to solve. I'm going to collect my x terms over here on the right-hand side. So I'll have 7x minus 8 is equal to 6. I'll bring my constants over here to the left. So 14 is equal to 7x, and finish up by dividing both sides by 7. So my answer I have is x equals 2. Again, I want to check to make sure that that works in the original equation. So is the cube root of 2 plus 6, is that equal to 2 times the cube root of 2 minus 1? Well, over on the left-hand side, I'm left with 2 plus 6 gives me 8. So the cube root of 8, again, that is 2 times 2 times 2. So this side equals 2. Is that equivalent to 2 times the cube root of 2 minus 1? That gives me a 1. And we know the cube root of 1 is also 1. So is 2 equal to 2 times 1? Well, 2 is equal to 2. That's good. So my solution is x equals 2.
Okay, so let's take a look at example 3. You're solving equations with rational exponents this time, and a hint: when you are doing this to find a power, you want to multiply the exponents. Here's an example. If you have x plus 12 raised to the 1/2 and you're raising the whole thing to the 2nd power, then remember, when you raise a power to a power, you're multiplying those exponents. So it ends up being x plus 12 and raised to the 1/2 times 2. 1/2 times 2 is just 1, so we're really left with x plus 12 to the 1st. And that's the goal here, is to get the exponent to be 1. Like in this example, our exponent is 1/3. We don't want that. We want the exponent to be 1. So the way to get that to be a 1 is to raise both sides of this equation to the reciprocal of that exponent. So we're going to raise both sides to the 3rd. So we get 5x plus 7 raised to the 1/3 times 3. So that's just going to be 1. So I get 5x plus 7 to the 1st. And that's equal to 3 cubed, which is 27. I subtract 7 from both sides. I get 5x equals 20. Dividing by 5, I get x equals 4. And if we do a little check on this, it's 5 times 4 plus 7 raised to the 1/3, and that's equal to 27. I'm sorry, no it's not. Is that equal to 3? I'm going back to our original equation. And so I get 20 plus 7, that's 27, raised to the 1/3. Is that equal to 3? Sure, because this is, as we learned earlier, that's the cube root of 27, and the cube root of 27 is 3. So it does work, and we like our solution of x equals 4.
All right, our next example here. So example B kind of showing us another problem similar to this. Again, you notice you have the quantity 4x plus 8 raised to the 1/2. So I want that side to become a power of 1 raised to it on that side. So I'm going to multiply both sides by the reciprocal. So the reciprocal of 1 over 2 is going to be 2 over 1.
Raise both sides to the reciprocal.
Yeah, raise both sides to the reciprocal. So I'm going to think about when I multiply my exponents here. So if I'm going to multiply the exponent of 1/2 and the exponent of 2, that's going to become 4x plus 8 raised to a power of 1, or just 4x plus 8. And that is going to equal, if I square the quantity 2x, remember that's really like 2 squared times x squared. So this is going to equal 4x squared. Now, I don't have a linear equation anymore. I have a quadratic. So when I solve quadratics, I always want to have one side equal to 0. So I'm going to bring everything over to the left side here. So 4x squared minus 4x minus 8 equals 0. Now, I notice all three of those terms have a common factor. They all have a 4 in common. So I might start off by dividing that out, or factoring it, I should say. So I'll be left with x squared minus x minus 2 equals 0. Now, in order to solve that, that sets us up pretty nicely for product sum. Remember, my product in this case is always a times c. So that's going to be 1 times -2, or -2. My sum is my b value. My b value in this case is -1. So two numbers that multiply -2, add to -1 will be -2 and +1. Kind of carrying up over here on the side. I had a 4 out front, and I'm going to product sum. Now I can use that shortcut since a was 1, x minus 2, x plus 1 equal to 0. Now I wanted to solve for x, so I have this factor could have equaled 0, so one potential answer is x equals 2. My second factor equal to 0. I'll subtract that 1 over, so x equals -1. Again, I'm not going to set that 4 equal to 0 because 4 can never equal 0. There's no answer I would get from there. So this leaves us just with our check to see if these work, if both of them work, one of them work, where we end up with. So let's check 2 first. So 2 times 2, again plugging in the original, is that equal to the quantity 4 times 2 plus 8 raised to the 1/2 power? Well, is 4 equal to 4 times 2 is 8. 8 plus 8 is going to give me 16. So is the square root of 16, because that's what a 1/2 power is that equal to 4? Yes, that works. So that answer is good. Let's test -1 in our problem. So 2 times -1, is that equal, we're running out of room here, 4 times -1 plus 8 to the 1/2 power. So we're saying 2 times -1, -2, is that equal to the square root of what we have here? 4 times -1 is -4 plus 8. That becomes the square root of 4. So is it true that -2 is equal to the square root of 4?
No.
Hopefully we're saying that's a no. So remember, that's what we call an extraneous solution. So the answer x equals -1 did not work in the original problem. So my only answer is x equals 2.
All right, so that brings up your second notes must do. You're going to solve this equation, x plus 5 raised to the 1/3 equals 3. Don't forget you're going to raise both sides of this equation to the appropriate power so that you can get that exponent to be a 1 instead of a 1/3. And that's all we have for this video, so make sure you've taken good notes, make sure you've completed both of the notes must do, and we'll see you next time.